Thank you, Chairman, for the introduction. So, the topic of the presentation is an advanced investigation on LVRT strategy in wind integrated power system. The study has been done by one of my students, Ankit Jotwani, and what we are trying to see in this study is we are diving a bit deep into this LVRT requirement from wind turbines and trying to see whether there are any issues with the LVRT requirements that are being asked by different system operators or regulators across the world. I'll briefly give a bit introduction about this LVRT, how it came into picture in the beginning, and then how it has evolved over the decades. A bit brief about the types of wind turbines for those who while most of you will be anyway aware of the types, but just for the introduction purpose, there are three types of wind turbines: type 1, type 2, which are old technology, no more existing in the market at the moment because of various reasons. Now it is only variable speed type 3 and type 4 wind turbines that are in the market. So the issues with these wind turbines are in the past there was voltage dip in the grid led to the disconnection of wind turbine generators owing to different reasons. As mentioned here, mechanical stress, over voltage in DC line converter, overcurrents, islanding, and all that. So to specify more about this requirement of LVRT, it can be divided into two subsections. One is steady state requirement, one is dynamic requirement. Steady state requirement of reactive power support or voltage control or other controllers, for example, FRT, frequency ride through, as well. Power quality indices have been in place, and then there are the dynamic requirements. For example, voltage ride through, UVRT, LVRT, frequency ride through, again higher frequency ride through, lower frequency ride through. Those are the dynamic requirements from the wind turbines. The grid code, as you see here, has started grid code for wind. So when we say grid code, is primarily grid code for wind or solar maybe, but the grid code for conventional power plants has been in place for a long anyway. So the grid code for wind started way back in 1999 to 2000 in Denmark and Germany. E.ON, who used to be the TSO, one of the TSO in Germany, it started from there, and Danish TSO, Elkraft, now it's Energy and Decay. And over the years, so initially it was the requirement of what we consider them as a lenient LVRT requirement, grid code requirements. And then over the years, the more and more stricter grid codes have come for the reason that the penetration level of these renewables has grown significantly. So initially, for example, the wind turbines were allowed to operate, were allowed to have simple on and off operation because the penetration level was not that significant. So even if for the sake of their protection, they were allowed to simply back up from the grid if there was any disturbance in the grid. But as these system operators over the years realized that now the level of the penetration of this wind or solar is getting more, we cannot allow to have simple on and off operation because that can lead to a significant outage of the generation in the system and may lead to some stability issues in the grid. So as a result, the grid codes have evolved, and as we see, we have different LVRT requirements from different countries, depending on the grid. It depends on the grid whether the grid is weak or it's strong, or it is a small islanded system or it is a large system. So depending on those different factors, the LVRT requirement of different countries is different. As you can see from here, from the LVRT curves from different countries, it varies significantly. If we see, if we try to now go deep into the LVRT requirement or from wind turbines, it can be divided into two categories. One is reactive power priority based LVRT, where the wind turbine is required to inject reactive power, reactive current into the grid during a voltage event, during a voltage dip in the system. So this reactive power priority LVRT grid code is followed in most of the countries, and the other requirement of this, the LVRT requirement, which is different than this reactive power based LVRT, is that it's known as active power priority, where during the fault, during the voltage dip, the wind turbine is not supposed to give priority to the reactive current injection. Rather, it is supposed to give priority to the active current injection during the voltage dip. So it means the priority goes to the active power injection to the grid during this LVRT event, during the fault and following the recovery of the voltage. So few countries follow this active power priority LVRT scheme, where the wind turbine is required to inject active power with first priority, and then reactive power is of course expected to help in the voltage recovery, but within the left out margin, the first priority goes to the active power. So for example, Ireland, Alberta, and India is also having active power priority LVRT requirement. So the main objective of this study is this active power priority LVRT requirement from system regulator. The intention for this active power priority is actually to have to support the grid frequency. For example, in islanded systems, a small systems, frequency becomes much more of a concern than voltage. For voltage support, they may have local infrastructure to have better voltage control, but the shortfall of active power during this voltage event can have more significant impact on the frequency given the size of the system. So their priority goes more to the active power injection to the grid during this voltage event rather than to the reactive current. So our main objective of this study is to see if we follow this active power priority in the countries where this active power priority based LVRT requirement is there, will it always result in active power, greater active power injection than reactive current, than reactive power priority LVRT? That is the main purpose of this study. If it is always going to lead to the intended results in the system. So this a bit again about how the LVRT has evolved over years in Germany and Denmark. If you see 2004, this dashed line in German TSO, tenant TSO, initially it was 15% dip. Below 15% of voltage dip, the turbine was allowed to disconnect from the grid. Now if you see, it is zero voltage right through, because now the penetration level is significant. So the system operator cannot afford to have a significant portion of wind going out of the system if there is a severe fault in the system. While as if you see, the recovery has improved over the years. For the past one, 2016, this grid code requirement, the recovery time is up to 3 seconds, while as now it is fast, 1.5 seconds. The reason primarily is in the beginning, in the previous years, like let us say 2000, 2003, around that time, there was significant penetration of these type 1 and type 2. Induction generator based these wind turbines, and these induction generator based wind turbines were leading to the weak grid, because induction generator will draw heavy reactive current from the system during a fault, during a voltage dip. So that was the reason that the system was expected to have slow recovery. But now over the time, those type 1, type 2 wind turbines have been partly replaced by the new wind turbines, and the new, in addition to that, new type 3 and type 4 defig and type 4 full converter based wind turbines have taken the last share. So as a result, they don't have the issue of the drawing reactive power from the grid during the fault. So the recovery, if you see the recovery curve, has been stricken a little bit more. Same is applicable to the Denmark. So this is the LVRT curve of India. We have above 33 kV as well as Ireland, where we have active power priority during the fault voltage dip. So if you see here, above 33 kV in India, whichever wind turbine is connected to the grid, we have this LVRT requirement, as you can see here, and we have for different voltage levels we have different these time periods. This time period for the fault before which a wind turbine can actually disconnect from the system. But we don't have ZVRT, zero voltage ride through requirement here in India as well as in Ireland. This is a modeling of the wind turbine that we did. We implemented this type 3 defig based IEC 614000271 model, and then we try to see how it actually affects the system if we stick with this active power priority LVRT requirement. This is a small case study system here. If you see, there are some induction motors, synchronous generator, and wind power plant in this system, and some constant load, constant power and constant impedance load in this system. These are the expected results. If you see the left top, this voltage curve, in the two cases, we try to compare reactive power-based LVRT as well as active power-based LVRT curve. In the two cases, if you see, active power priority LVRT is intended to have more penetration of active power during the fault. As a result, better frequency during the fault. That's what is expected. If you see the left bottom plot, the wind turbine is actually pumping more active power during LVRT period for active power priority LVRT requirement. While as for reactive power priority LVRT requirement, the active power injection during this LVRT period is relatively less. That is what actually is expected from this. That is the intention as well. So if you see the frequency of the system left top, in the reactive power priority case, in this reactive power priority is expected to be active power priority is expected to be better, and that is what is actually reflected in this figure. Active power priority case frequency is better than reactive power priority case LVRT. Now this is what we were intending to see, the unexpected results. While the intention of this active power priority LVRT is to improve the frequency during LVRT, but that seems to be in some particular cases having opposite impact, opposite results basically. In this case, because of this voltage, because active power injection depends on voltage and current. So voltage, product of voltage and active current that is being injected in the grid. But if we have now, so it is a product of two quantities, voltage and active current. Now if we have predominant increase in voltage compared to the decrease in current, then we can have probably more active power injection. And reverse is also true. That's what is happening in reactive current priority based LVRT in some cases. That during the fault, the improvement in voltage is relatively higher than decrease in the current, active current injection during the fault. As a result, the product of the two, which is the active power injection to the grid, is more during reactive current priority LVRT rather than active current priority LVRT. So we try to see same effects on the larger system. You can see here these are again expected results on reactive power priority LVRT case. We have less active power injection into the grid during the fault. As a result, the frequency is poor in case of reactive power priority based LVRT requirement, while as in active priority based LVRT requirement, frequency is better in the grid. But then again, that unexpected result here in this case, we have more active power injection into the grid in case of reactive power priority LVRT rather than active power priority LVRT, where we are intending to have better active power injection into the grid. So it kind of it has opposite effect in some particular cases. So it is really important to see how to actually look into these issues. So this is again somewhat similar case study where it is showing the same results as unexpected. So the point here is, while we intend to have more active power injection into the grid during this active power based LVRT requirement, it happens in some cases so that the active power injection during reactive power based LVRT is better than in active power priority based LVRT. So now we are trying to see can we design a method which can actually sort of predict which type of LVRT priority we should follow to have active power injection more during the entire voltage event. So yeah, so it tries to highlight deeper issue into this LVRT requirement that we follow across the globe. Two types of LVRT requirements: active power and reactive power. And yeah, as the study highlighted that we need to really look into this requirement of active power based LVRT, particularly in some special cases where it actually has opposite results. Thank you.